all. This is a video for the first half of section 42.3 in your Springboard book, which starts on page 627. The first thing that it starts out with is called the fundamental counting principle. The fundamental counting principle says that if one event can occur in m different ways and a second event can occur in n different ways, then together the event can occur in m times n different ways. So we've used this before, we just didn't know it was called the counting principle. You have 4 shirts, 3 pairs of pants, and 2 jackets. How many outfits can you make? So in order to do that, if you were using this counting principle, all you would have to do is say, okay, I have 4 choices for shirts, 3 choices for a pair of pants, and 2 choices for jackets. So to get my outfits, I would take 4 times 3 times 2, and I would get 24 different outfits that I could make. Okay. Now we're going to learn about some special notation here, n factorial. And n factorial is n with an exclamation mark after it. It said n factorial. And basically it means the product of n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. So let me give you some examples of that. So if you have 5 factorial, that means you start at 5, so it's 5 times 4 times 3 times 2 times 1. That's 5 factorial. And if you put that in your calculator, you get 120. 7 factorial is just 7 times 6 times 5 times 4 times 3 times 2 times 1. And if you put that in your calculator, you would get 5,040. Sometimes you'll be asked to solve a problem that looks like this. 10 factorial over 5 factorial times 2 factorial. So if you had to solve a problem like this, the way that I would do it is I said, okay, well, I know 10 factorial is really 10 times 9 times 8 times 7 times 6 times, 5 times 4 times 3 times 2 times 1. 5 times 4 times 3 times 2 times 1 is the same as 5 factorial. So I wrote 10 factorial as 10 times 9 times 8 times 7 times 6 times 5 factorial because I also have a 5 factorial on the bottom. And now I can cancel those two. And I end up with 10 times 9 times 8 times 7 times 6 over 2 factorial. 2 factorial is 2 times 1. So I have 10 times 9 times 8 times 7 times 6 over 2 times 1, or divided by 2. And if I do that in my calculator, I get 15,120. So let's use our counting principle that we just learned here. And we're going to learn a definition here. A permutation P is an ordered arrangement of a set of objects. Okay? And a permutation order is important. So this question says, in how many ways can you arrange the letters in the word math? So I have 4 spaces here because there are 4 letters in the word math. And so before we go into how to do this, so one arrangement of the letters of the word math would just be math. Okay? Another arrangement would be M-A-H-T. Another arrangement, for example, would be M-H-A-T. Another arrangement would be M-H-T-A. Another arrangement would be M-T-H-A. Another arrangement would be M-T-A-H. Another arrangement would be T-M-A-H. So when it says arrangement, I just want to know how many different ways can I write these letters. So if I'm doing that, and this is not all the possible choices, by the way, but if I were doing this, I would think to myself, okay, if I'm arranging the letters in the word math, for the first letter here, I have 4 possible choices. I could choose either M, A, T, or H. But then when I get to the second letter, I only have 3 choices because I've already picked one. So I have 3 choices left. When I get to the third letter, I've already picked 2 letters, so I only have 2 choices left. And finally, for my last letter, I have 1 choice. So if I wanted to know the number of the ways that I could arrange the letters in the word math, it would be 4 times 3 times 2 times 1. And that is 24. So if I wrote out all the possible arrangements of letters in the word math, there would be 24 of them. And notice that 4 times 3 times 2 times 1, that is the same as 4 factorial. All right, so I'm going to look at a second example. This example says 5 children line up for a family portrait. How many different ways can the children line up for the portrait? Okay, so the same thing. If I'm the photographer, I have 5 children. I'm going to call one of them over to stand in that first place. And I have 5 choices for which child I pull over to stand in the first place. But then I have 4 choices for the child that will stand in the second position. Then I only have 3 choices. Then I have 2 choices. And then I have 1 choice. So the number of different ways the children can line up for the portrait is 5 times 4 times 3 times 2 times 1. And so if you do that in your calculator, you get 120. And once again, notice that this is equal to 5 factorial. So there is a formula for this. It says the number of permutations of n distinct objects is n permute n equals n factorial. So what that means is I'm taking n objects and I'm arranging all n of them. It will be n factorial. So in this example, I had 5 children line up for the family portrait. I'm arranging all 5 of them. Okay? And so that's going to be 5 factorial. I have 4 different letters in the word math. I'm arranging all 4 of them, so that is 4 factorial. Now, I'm going to go back to this example of my picture, and I'm going to say, suppose now that these children can be seated on a bench. How many ways can 3 of the 5 children be seated on a bench? So if I'm looking at this, I would say, okay, I'm the photographer. The first seat on the bench, I have 5 choices for whoever sits there. Then the second seat on the bench, I have 4 choices for who's going to sit there. And finally, my last seat on the bench, I have 3 choices. So the number of different ways that 3 of the 5 children can be seated on a bench is 5 times 4 times 3, which is 60. Okay, so there is a formula for permutations that says the number of permutations or arrangements, P, of n distinct objects. So this word distinct is important. Okay? So this word distinct means separate, different. Okay? Of n distinct different objects taken r at a time is given by the formula n permute r equals n factorial over n minus r factorial. So in this example with the bench here, I have 5 children and I'm taking 3 of them to put on a bench. So if I were going to write that, it would really be 3. Whoops. I have it over here, I guess. So I'm writing that. I have 5 children and I'm going to take 3 of them to sit on a bench. So that's really going to be 5 permute 3. I'm taking 3 at a time. Okay? So that's equal to n factorial, so 5 factorial, over n minus r, so in this case 5 minus 3, 5 that I'm taking 3 at a time. 5 minus 3 is 2, so 5 factorial is 5 times 4 times 3 times 2 factorial, divided by 2 factorial. The 2 factorials cancel, and I would get 5 times 4 times 3, or 60. The same thing that I got up here. So if you have n distinct objects and you're taking r at a time, you can use this formula. All right, now, this example is a little bit different. It says, how many ways can you arrange the letters in the word Tallahassee? So if you look here, I have 11 blanks because if I count the letters in the word Tallahassee, there are 11 of them. And so before, when I did the word math, for example, I just took, I said there were 4 choices for the first letter. So in Tallahassee, there's 11 letters. So 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But there's a difference. Not all of these letters are distinct. Some of them, you have 3 A's. So not all the letters are distinct. You have 2 L's. So you have 3 that are letters that are of the kind A. You have 3 letters that are of the kind L. 2 letters that are of the kind L. 2 letters that are of the kind S. And 2 letters that are of the kind E. When you have that, if you just do 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, you will count too many different arrangements because you have 3 A's and 2 L's and 2 S's and 2 E's, and they're not all distinct. So when that happens, you're going to have to divide out those arrangements that will be repeated because not all your letters are different. So in order to do that, there's a formula here, and it says, and we're going to come back because we're not done with this problem, but it says the number of permutations P of n elements taken n at a time, so that means you're going to arrange all n of them. So I'm arranging all 11 letters of the word Tallahassee. With R1 like elements of one kind, R2 like elements of another kind, and so on, is given by the formula P equals n factorial over R1 factorial, which is our elements of one kind, R2 factorial, like elements of another kind, R3 factorial, elements of another kind, and so on. So in this case, with the example Tallahassee, I'm going to have to use this because I have all n elements, okay, taken n at a time. In other words, I'm arranging all of them, but I have some like elements here. So to solve this particular problem with my 11 letters in the word Tallahassee, I would have 11 factorial on top. And then on the bottom, okay, I have R1 like elements of one kind. So I'm going to come up here and say, okay, I have 3 A's. So I have 3 elements that are of the kind A. So I'd have 3 factorial there. I have 2 L's. So I'm going to put 2 factorial here for my L's. I also have 2 S's, so that's another kind, 2 factorial. And 2 E's, that's another kind, 2 factorial. Now I also have 1 T and 1 H. So I could say 1 factorial here for T and 1 factorial here for H. But 1 factorial is just 1. So I don't have to put that there. So I've used my formula, so I divide out those arrangements that would be the same because not every letter is distinct. So to solve this, if I were going to solve this, I would do 11. So 11 factorial is 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times, okay, and it'll be 3 times 2 times 1. But I'm going to stop here at 3 factorial because I have a 3 factorial on the bottom, and I can cancel those two, 3 factorials. So when I cancel the 3 factorials, I would end up with 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4. And so then on the bottom, I canceled my 3 factorials, so I would have 2 factorial times 2 factorial times 2 factorial. And so 2 factorial is 2 times 1. So this right here on the bottom is really 2 times 1. I didn't change that. It's the same as 2 times 1 times 2 times 1 times 2 times 1. So 2 times 1 times 2 times 1 times 2 times 1, that's 8. So I would have 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4. That's over 8. Okay. And so because I have an 8 in the top and in the bottom, those can cancel. And so what I'm left with is 11 times 10 times 9. Now remember my 8's canceled from the top and the bottom. Times 7 times 6 times 5 times 4. So when I do this and I get my answer, I get 831,600. So that's how many ways you can arrange the letters in the word Tallahassee. All right, and there's that formula that we use to do that. So we've already looked at this formula. So again, if you have n distinct objects, take an r at a time. The formula is n per mu r equals n factorial over n minus r factorial. So we have one more example that's different, and then we're going to use this formula quite a bit for a couple more examples. So this example says you're making a 3-digit secret code with the 4 digits 1, 3, 5, and 7, and any of these digits can be repeated or replaced. How many codes are possible? So when it says any of the digits can be repeated or replaced, basically what that means is that 555 would be a possible code in this case because you can repeat the 5s. So you're making a 3-digit secret code. So in order to do this, I have 3 places here. And I have 4 choices for my first digit, but I also have 4 choices for my second digit and 4 choices for my third digit because the digits can be repeated. So in this case, the number of different ways to do that would be 4 times 4 times 4, which is 64. So that's kind of a special problem. So let's do a couple more examples where we use our formula up here. So this says, how many different ways can 8 children be seated in a row of 5 chairs? So basically what this is I have 8 children, and I'm going to take 5 of them and arrange those 5 children. So that's 8 permute 5. And the formula says that's going to be 8 factorial over n minus r, so 8 minus 5, which is 3 factorial. So to solve that, remember 8 factorial is just 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So 8 times 7 times 6 times 5 times 4 times, and instead of writing 3 times 2 times 1, I'm just going to write 3 factorial because that's what 3 factorial is. And then my 3 factorials will cancel. And the answer here would be 8 times 7 times 6 times 5 times 4, which is 6,720. My next example says, how many 5-digit zip codes are there with no repeated digits? That means each digit is distinct. And so remember, it's the number of permutations of n distinct objects. So separate objects. Take an r at a time. So since none of the digits can be repeated, they're distinct objects here. So how many 5-digit zip codes are there with no repeated digit? Meaning every digit that you take is a different one. So total, there are 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? If you look at those digits, you count. There's 10 of them. 0 to 9, there are 10 digits. So in this case, this would be 10. And I'm going to arrange 5 of them. So 10 distinct objects. I'm arranging 5 at a time. So the equation tells me that will be n factorial. So in this case, I will have 10 factorial over n minus r factorial. So 10 minus 5 is 5 factorial. So when I go to write this out, I would have 10 times 9 times 8 times 7 times 6 times 5 factorial. On the bottom, I would have 5 factorial. My 5 factorials will cancel. So this will be equal to 10 times 9 times 8 times 7 times 6. So 10 times 9 times 8 times 7 times 6. And that is 30,240. Okay, and so notice that's the same as if you thought about this and you said, okay, I need 5-digit zip codes. So 1, 2, 3, 4, 5. There are no repeated digits. So when I'm making my zip codes, I have the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 to choose from. Those are all the digits. None of the digits are repeated, I'm told. So for the first one, I have 10 choices because there are 10 digits. Then for the second one, because none of the digits are repeated, I would only have 9 choices. And for the third digit, I would only have 8. And then 7 for the fourth and 6 for the fifth, which is the exact same thing that I got using the formula. 10 times 9 times 8 times 7 times 6. Okay? My last example says 6 people are in a contest. In how many ways can first and second place be awarded? Okay, so you have a first place and a second place. So if you were looking at this and you didn't use the formula at all, you would say, okay, well, for my first choice here, I have 6 choices because there's 6 people. And for second place, then I have 5 choices because I've already chosen one of the people. So that would give me 6 times 5, which is equal to 30. I could have also used my permutation formula. And so I could have said, okay, this is the same as 6 sorry about that. It's the same as 6 permute 2 because I have 6 people in a contest and I'm choosing 2 things, first and second place. So if I look at that, that is equivalent to 6 factorial over 6 minus 2, and minus r is 4 factorial. So if I work that out, I know that 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. But I'm going to write this as 6 times 5 times 4 factorial. Because on the bottom, I also have a 4 factorial. And so the 4 times 3 times 2 times 1, or the 4 factorial, will cancel. And that will leave me with 6 times 5, which is equal to 30. All right, so for tonight, you just have 5 homework problems here that I would like you to try. And that is all. Thank you.